Welcome to the fascinating world of quantum mechanics and nanotechnology. In this video, we will explore how QTCAD, a powerful simulation tool, helps us solve the Schrödinger equation for a quantum dot. Let's dive in. Let's learn about prior concepts being used in this simulation. If you talk about quantum dots are tiny semiconductor particles that confine electron in three dimensions. Their unique property make them key player in cutting-edge technology like quantum computing and advanced photovoltaic. It is a 3D rectangular geometry being used in this simulation. In this simulation, this geometry is split into five parts: two leads on the end and two barriers between the leads, and the central region and quantum dot in the middle. This layout represents how electron might travel through a nanoscale devices. The solver being used in this simulation are Schrödinger solver. Schrödinger solver deal with the quantum mechanical behavior of electron. Its purpose to solve the time-dependent Schrödinger equation for quantum dot system, determine the eigenenergy and eigenfunction of the quantum state, and role in this simulation are the Schrödinger equation help us understanding their behavior, the quantum dot region to capture quantum confinement effect, providing accurate energy level and eigenfunction of confined electron. But how do we solve it for nanoscale devices? The answer is QTCAD. To unlock the full potential of technology in both classical and quantum behavior must be understood. That's why a QTCAD, a powerful simulation toolkit, is used. Let's talk about the workflow of QTCAD software. First, device specification. First, we create the geometry of the device being used in this simulation. First, we create the rectangular piece by giving shape, dimensions, and some physical names. After that, we create mesh using geometry file of the device. Third step where QTCAD comes, where we define solver, material, constants, and some parameters being used for this simulation. Better visualization and analysis, we use PyPlot, 5-star, or ParaView. Let's jump to the code. As you remember from the workflow of QTCAD, the first step is create geometry. I created earlier. Let's open in Gmsh software. To open Gmsh software, let's move to the command prompt and then move to the directory of QTCAD. Copy the path of QTCAD directory. Copy the path and move to the command prompt and paste. Then activate the environment which created earlier. It's moved from base environment to QTCAD environment. Let's open the Gmsh software with command gmsh open. Our Gmsh software is open. Let's open the geometry file. In example tutorial, in message file I store my geometry file with name lead.lead. Let's open it. It is a 3D rectangular prism that is split into 5 parts: two leads on the end and two barriers between the leads, and the central region and a quantum dot in the middle. This layout represents how electron might travel through a nanoscale device. Look at the 1D meshes. For the better visualization, go to the tool option, geometry and visibility. Click the surface level, volume level and physical name. Here you can see the lead, barrier, dot region, barrier 2 and lead 2. Lead represent region where electron can freely move in and out of the device. These are positioned at the two end of the prism. And if you talk about barrier, it acts as a energy obstacle that electron need to overcome to move between the lead. Its position between the lead and the dot. And if we talk about the dot region, the central region representing a quantum dot. Let's look at the 2D mesh, then 3D mesh. If we close the application, the mesh file already stored in same folder. Here you can see our mesh file is stored in the same folder. From the workflow of QTCAD, our two-step is complete. Now it's time to the third step where QTCAD comes. Let's open the VS Code and run the simulation. I had already written the program. Let's see what it means. I import numpy as a NP for numerical operation. After that, matplot library for plotting and pathlive for handling the file path. After that, we import mesh submesh from QTCAD device module. Mesh class is used to load and represent 3D mesh. A mesh is a collection of nodes and elements that define the geometric and spatial properties of the device. In QTCAD, meshes are typically used to model nanoscale devices, and submesh a subset of the full mesh focusing on a specific region. This allows for more targeted computation and analysis within particular area of the device. After that, we import constant as a CT. Constant is used for predefined physical constant that are frequently used in device modeling and simulation, like elementary charge and Boltzmann constant. After that, we import line cut from QTCAD device analysis module. Line cut function that extract data along a specified line through the mesh or device. It is useful for analyzing spatial dependent properties such as wave function probability, potential energy distribution. If you want to examine the variation of potential energy along the x-axis, line cut allow to define start and end point of the line and extract the corresponding data. After that, we import I/O from QTCAD device module for providing input-output function for saving and loading data. After that, we import material as a empty. Material define physical and electronic properties of the material. Like in this simulation, material is gallium arsenide. Gallium arsenide often used in quantum dot modeling due to its favorable band gap and electronic properties. Silicon is also used in semiconductor devices. By using these material definition, the simulation can incorporate specific properties like effective mass and permittivity relevant to the material. After that, we import device and subdevice from QTCAD device module. Device represent the entire physical system being simulated built on the mesh structure. The device class allow you to assign material to different region of the mesh and define physical property like potential energy and carrier type. And the sub-device, a subset of the full device created from a submesh, allow for localized simulation such as solving for quantum state with a specified region like quantum dot. After that, import solver and solver parameters from QTCAD device Schrödinger module. Solver implement the Schrödinger equation for quantum mechanical calculation within the device. It's compute the eigenvalue and eigenfunction of the system, and solver parameters configure the parameter for the Schrödinger solver. This combination of solver and solver parameters enable precise quantum mechanical modeling of nanoscale devices such as quantum dot or nanowire. After that, we define path for the mesh file and output file related to the script directory, like from where we have to load the mesh file and where our output is being stored. The names like creating.bto file. After that, we have to load and plot the mesh scaling factor, convert the dimension from meter to nanometer. After that, mesh is used to load the mesh and mesh.show function is used to show the mesh file. After that, we create a device from the mesh. Carrier will be electron. That we define material for the 5 different regions for rectangular prism like dot region with gallium arsenide, lead also gallium arsenide, and lead 2 also gallium arsenide, and barrier 2 also gallium arsenide. After that, we define the potential, we define the energy landscape within the device using QTCAD. We specify the quadratic potential along the y and z axis add potential barrier along the x-axis. These barriers create a confinement necessary for a quantum dot state, like potential along y and z axis. Here y0 and z0 define the position of the minimum of the harmonic oscillator potential along the y and z direction. After that, ky and kz define constant for the parabolic potential along the y and z direction. After that, V function xyz define the potential energy function as a sum of parabolic potential in the y and z direction. After that, set the potential energy for the device using the predefined potential function V function. After that, add the potential energy along x-axis. It means we have to add constant potential energy around different regions like barrier 1, barrier 2, lead and lead 2. After that, we have to create some mesh in dot barrier and barrier 2 region. After that, create a sub device from the full device and the sub mesh. After that, solve the Schrödinger equation, configure the Schrödinger equation and give the number of energy level to consider. Here we given 3. After that, set the tolerance for convergence and use the solver for solve the equation and print the energy. After that, create a global node in dot region and in full device. After that, line cut coordinate for wave function and potential energy. Here, begin WF and end WF. Begin wave function and end wave function indicate the beginning and end point for a line cut of the wave function along the x direction. In the same way, begin potential energy and end potential energy indicate the beginning and end point for a line cut of the potential energy along the x direction. After that, line cut of a ground state squared and potential energy. Here, psi position x and psi x0 indicate a line cut of the ground state is wave function squared along the x direction, and v position x and Vx generate a line cut of the potential energy along the x direction. Begin y and end y define the beginning and end point for a line cut along the y direction. In the same way, generate a line cut of the ground state wave function squared along the y direction. After that, we have to set the nanometer scale factor and plotting eigenstate along x-axis. First we have create a figure and axis for plotting, and after that set the title of the plot. After that, plot the ground state wave function squared along the x direction and create a twin axis for plotting the potential energy, and plot the potential energy along the x direction and add grid to the plot. And after that, set the x-axis label and set the y-axis label for the wave function and set the y-axis level for potential energy in electron board. After that, we have to display, ensure the plot layout is tight and display the plot. In the same way, plotting eigenstate along y direction and display and save in BTU format for better visualization in ParaView. Let's run the simulation. Load the mesh file of rectangular pitch 5 different area, center region, lead 2, dot, and barrier 1, barrier 2. And it calculated the 3D mesh statistic and submesh statistics. Here region physical names, lead, barrier, dot, barrier, lead 2, 5 different region. After that, solving Schrödinger equation, calculate the energy level in electron volts. Here line cut along x-axis and label wave function in y and x in nanometer, and twin axis here is potential in electron volt. Here line cut along x direction. Let's see line cut along y direction. In y axis wave function and x axis nanometer, and here electron volt twin axis potential energy. And our output file, the BTU file is stored in the output folder. Let's open the file explorer and see where output file is stored. Go to the file explorer in C drive. Go to the QTCAD folder, then example, tutorials and output. Here you can see .btu file is stored here. And that's how we use QTCAD to solve the Schrödinger equation for a quantum dot. From setting up the device to visualizing wave function, we have seen the power of QTCAD in action. Thank you for watching and see you next time.